Hello everyone, in this video we're going to be learning about gravity and we're going to dive deeper into that. So what is universal gravity? Well, universal gravity is equal to F equals G, which is a constant, times the masses and the distance between the masses. This distance is taken from the center of the masses. So for example here, the distance between them, as you can see here, is denoted from the center of the first mass to the center of the second mass. The constant g represents the universal gravitational constant, which is equal to 6.67 times 10 to the negative 11 meters cubed over kilograms second squared. Now is a good time to talk about universal square law because we see an implication of it here. Well, universal square law means that, universal square law indicates that as the distance between two masses increase, the force between them decreases by a magnitude of 2. So as you can see here, the exponent 2 is the reason why it's called inverse square law, because it's inversely proportional to the force by a square of the radius or the distance between the two masses. Now let's answer a simple question. Calculate the resulting force of gravitational attraction between two masses if one of the masses was to double and the distance between them was to triple. So let's put the formula down. Okay, so we know that one of the forces is gonna double, so this is gonna double, and the distance between them is gonna triple, so triple, and as a result of that we get g 2m and m over 9r squared. So the resulting force is 2/9 of the original force. Now let's talk about gravitational fields because they're the reason why gravity exists. So we know that g is equal to 9.8.1 or simply 10. The g represents the acceleration towards the center of the earth. So on earth, the gravitational field is towards the surface of the earth and the vectors are perpendicular to the surface of the earth. Well, now you might be thinking, well, the earth is round. How can we take them as perpendicular vectors? Well, we take them as a small point on the surface of the earth, and at that point the vectors are perpendicular to the surface of the earth, or that's what we assume. So gravitational fields, what causes masses to get attracted to each other. Now let's talk about a formula that we have been using a lot. F equals mg represents the normal force of an object, and we have seen this concept in kinematics and dynamics. Now let's talk about what g really means. So from F equals ma, which is Newton's second law, we know that g is equal to a. So g is actually an acceleration. And we know that the total gravitational force is g times mass 1, mass 2 over r squared. And here we can see that the mass is here. So the g has to be without this, right? So g is equal to the big G, the constant, big mass over r squared. So by looking at this formula, we can infer that the gravity of a certain object or a planet is not about the mass of the object that is on top of the planet, but it's about the mass of the planet itself. So the gravity for an elephant is the same as a human. Here, again, we should imply that the distance between forces are taken from the centers of the forces. So the gravity at 3r distance from the center of the earth is going to be calculated with the formula if we plug in the numbers. So the gravity, g times the mass of the planet, in this case I think it's earth, and 3r squared here as well. And again, here we see the inverse square law. Now we know how to calculate gravity. Let's calculate the surface gravity of the moon, okay? We have the mass of the moon and the radius of the moon. So we're trying to find, for example, if we were to be here, kind of like Neil Armstrong or Buzz Aldrin. Unfortunately, we're not because there hasn't been a moon program in a while, but I think there's a new program called Artemis to go to the moon. So we're quite stoked about that, but whatever. Let's calculate the gravity on the moon, on the surface of the moon. So let's put down the formula. G is equal to m over r squared, and we know that g is equal to 6.67 times 10 to the negative 11th times the mass is 7.36 times 10 to the 22nd over the square of 1.74 times 10 to the sixth, and I'm going to use a calculator for that, and I get 1.62 because it's an acceleration. And we see that on Earth the gravity is 9.81, so G Earth, and on the moon it's about 6 times less than that. Okay, now let's talk about circular orbits. So we know that Newton is the guy who found gravity, right? And he also contributed another thing from this new discovery. So think about this, okay? So you're on top of the world, and when you throw a ball horizontally, it goes down in the shape of a parabola, okay? But if you happen to throw this ball so fast that when it goes down, the curvature of the Earth goes down too. And this is how we found circular orbits, and this is literally how we found send objects to the space, to the orbit, and that's the reason why the ISS, International Space Station, works. So, for example, we have a ball, and we throw this ball, okay, so fast that when it goes down, okay, let's start here. We throw it horizontally, and when it goes down with the curvature of the ball, and it keeps doing it all the time because it's fast enough to go down the curvature of the Earth. Now, you might be asking how fast it should be, and we find this by referring to the formulas of circular motion. So if you haven't seen a circular motion video, I suggest you do it now. But to summarize everything, the acceleration of a circular motion is equal to the squared velocity of the object over the radius of the circle. Thus, the force of circular motion is equal to mass times v squared over r. So we have the force, but in order for an object to escape the gravity of the planet, for example of Earth, this force has to be at least equal to the gravitational force. So we know what the gravitational force is equal to. G equals m1 m2 over r squared. So we know that these are equal in order for the object to escape. So let's make them equal. And you know that this is the mass of the object, and this is the mass of the planet. So m1 is the mass of the object, and these cancel out. One of the r's cancel out. And as a result of that, we get g, the constant, the mass of the planet, over r, and this is equal to v squared. And we take the square roots of both sides. We get, so these cancel out, and we get velocity of the object as the square root of the gravitational constant, the mass of the planet, and r squared. So again, we know that the velocity of the object is not about the mass of the object, but it's about the mass of the planet. And you might also see that we found a velocity, not an altitude. So there isn't such thing as escape altitude. You can escape at any point. But in order to escape the gravity of the Earth, you have to be really fast because we're taking the square root of whatever the mass and the gravitational force is. So there isn't such thing as escape altitude, but there's escape velocity. And that's how the International Space Station or the rockets work. Let's do this question. Calculate the speed of an orbiting satellite around Mars at a height 3.57 times 10 to the 6th meters above the center of the planet. The mass of Mars is 6.42 times 10 to the 23rd kilograms. Okay, so let's put down the formulas. We have deduced the velocity formula. Now is a good time to use it. So velocity is equal to the square root of g, mass of the planet, over r. And we happen to have all of the variables, so let's just plug them in. So g is 6.67 times 10 to the negative 11 times the mass of Mars is 6.42 times 10 to the 23rd over 3.57 times 10 to the 6th. So I'm just going to use a calculator for the solution. And I get 3,487.86 meters over seconds. So in order for a satellite that is orbiting the moon at the altitude of 3.57 times 10 to the negative 6th, satellite has to be this fast. So you might realize that this is a big number, even for a planet like Mars. So at this point, I want to show you something. The International Space Station is orbiting the Earth, but you might realize that the objects orbiting planets has to be really fast in order to stay in the orbit. Now, let's take a look at the International Space Station. So the ISS is 408 kilometers away from the Earth, which is about 250 miles, and its speed is 7.66 kilometers per second. It's about 23,000 kilometers per hour, or about 17,500 miles per hour, which is very, very fast. Now, let's take a look at Kepler's laws. So Kepler was a scientist who lived between 1571 and 1630, apparently, and he lived in Germany, and he had some laws. So let's talk about them. So the first law is planets orbit the sun along an elliptical path where the sun is at one of the foci of the ellipse. So here's an example of that. So this is the shape of an ellipse, kind of like an egg, and it has two focus points, so two foci for plural. The second law is a line drawn from the sun to a planet would sweep out an equal area during an equal interval of time. So as represented here, if we take the time, the area is going to be the same because, I mean, this is a property of an ellipse, and this also gives us an idea about the speed of the object. So in order for an object here to cover the same area as this one, because this has a much more, so you can see that the height here, or the width, is much longer, but here it's much smaller. So the radius that has to be covered has to be much bigger here. So we can infer that the object has to be faster once it's closer to the sun. And we can also infer that the closer you get to the cause of the gravitational field, the faster you have to go. And we know that from the previous examples with the ISS and the satellites. Kepler's third law states that the square of the period of a planet's orbit is proportional to the cube of its radius and in its orbit about the sun. So this is just to show us some math here. His formula deduced that the square of period is proportional to the radius cube. Another application we see with Kepler's law is that with comets. So comets follow highly elliptical orbits around the sun. Halley's comet takes only a few months to get around the sun on its closest approach, but it takes more than 7 decades to reach its farthest point from the sun and then return. So it's really easy to move around here because you have to be really fast, and you just move around so fast in order to stay away from the gravitational field of the sun. But once you get here, the gravitational field is so low, so you don't necessarily have to go so fast. And thanks for watching this video.